Chapter 7. Steam Conditioning Valves.
Next, we turn to introduction and design.
In this chapter, I'd like to introduce steam conditioning valves. Steam conditioning valves are broadly divided into three categories: desuperheaters, which lower the superheat of steam; steam conditioning valves, which adjust both pressure and temperature; and turbine bypass systems. Superheated steam is an excellent energy source for generating mechanical power. However, in many actual field applications, steam that has been significantly cooled to near saturation is more useful. This is especially true for heat transfer applications. There are three reasons why precise temperature control is necessary. First, to improve heating efficiency. Second, to eliminate unintentional superheat that occurs during throttling. And third, to prevent downstream products or equipment from being damaged by heat. One way to lower the temperature is to install a desuperheater. A desuperheater is a device that lowers the temperature of steam by injecting a controlled, predetermined amount of water into the steam flow.
To achieve desuperheating efficiently, the desuperheater must be correctly designed and selected for the specific application. While it may look like a simple device, it must integrate well with a variety of complex thermal and flow dynamic variables to function properly. Controlling the amount of water injected means controlling the temperature of the steam, and for this, a temperature control loop is used. This loop consists of three parts. First, there is a temperature sensing device installed downstream. Second, a controller that interprets the measured temperature relative to the desired set point. And finally, the controller transmits a proportional signal to a water controlling valve and actuator assembly to meter the required quantity of water. Whether a particular desuperheater installation succeeds or fails depends on several physical, thermal, and geometric factors.
Among the factors affecting desuperheater performance, some are obvious and some are not. However, all of these factors impact the performance of both the device itself and the system in which it is installed, though to varying degrees. The first, and perhaps most important factor for efficient desuperheater operation is selecting the correct design for the respective application. Desuperheaters come in a wide variety of shapes and sizes, and they use various energy transfer and mechanical techniques to achieve the desired performance within the limits of the system environment. Figure 7. One shows several variations of desuperheater installations. The differences between the available types of desuperheaters and their expected performance will be covered separately later.
This shows typical installation configurations of desuperheaters used to control steam temperature.
Next, we turn to technical aspects.
Let's look at the physical parameters that affect the performance of a desuperheating system. These include installation orientation, spray water temperature, pipeline size, steam velocity, and equipment versus system turndown. Among these, installation orientation is a frequently overlooked but critical factor in system performance. Correct placement of the desuperheater can have a greater impact on operation than the style of the unit itself. For most units, the optimum orientation is in a vertical pipeline with the flow direction moving upward. However, this is the opposite of most installation methods commonly seen in industry today. Other orientation factors include pipe fittings, elbows, and any other type of pipeline obstruction existing downstream of the water injection point. Figure 7.1 illustrates variations in the installation of a desuperheater.
The second technical aspect is the temperature of the spray water. Spray water temperature has a significant impact on desuperheater performance. Although it goes against logical convention, high-temperature water is actually more advantageous for cooling. As the spray water temperature increases, both the flow and thermal characteristics improve, which in turn affects the following items.
There are specifically three items that high-temperature spray water improves: drop size distribution, latent heat of vaporization, and vaporization rate. When the spray water temperature increases, all three of these areas are improved, enhancing the overall performance of the system. Meanwhile, the quantity of water to be injected has a directly proportional effect on the time for vaporization. Since the heat transfer process is time-dependent, the quantity of spray water affects the time required for complete vaporization and thermal stability. To determine the required spray water quantity QW as a function of inlet steam flow Q1, we use a simple heat balance equation. The equation is QW, mass, equals Q1 multiplied by the difference between H1 and H2, divided by the difference between H2 and HW. Here, Q is the mass flow in pph, and H represents the individual enthalpy values at the inlet, outlet, and spray water. Figure 7.2 shows the spray penetration.
This indicates how deeply the sprayed cooling water penetrates into the main steam flow.
I would like to introduce the method for calculating the spray water quantity based on the outlet steam flow Q2 for initial desuperheater sizing. Unlike the previous calculation based on inlet flow Q1, Q2 is the outlet flow, which is the combination of inlet steam flow and desuperheating spray water. In this case, the mass-based spray water quantity QW is calculated by multiplying Q2 by the ratio of the difference between inlet enthalpy H1 and outlet enthalpy H2 to the difference between spray water enthalpy HW and H1. To perform the basic CV calculation for sizing, the mass-based QW must be converted to a volumetric basis. In English units, this is done by multiplying the mass-based QW by 0.147 and dividing by the spray water density ρ_W. Here, the volumetric QW is in GPM, and ρ_W is the spray water density in lbm/ft3. After this conversion, the CV for each set of conditions is calculated by multiplying the square root of the volumetric QW multiplied by the specific gravity Sg divided by the differential pressure across the desuperheater delta PdSH. Sg is the specific gravity of the spray water, and delta PdSH refers to the pressure differential across the proposed desuperheater.
When designing a new desuperheater installation, I would like to introduce pipeline size as another consideration for proper system performance. As the line size increases, more attention must be paid to the penetration velocity of the spray and the coverage in the flow stream, as shown in Figure 7c. Some single-point injection-type desuperheaters have insufficient nozzle energy to disperse the spray throughout the entire cross-sectional flow area of the pipeline. As a result, the spray pattern collapses and thermal stratification occurs. That is, a subcooled center core becomes shrouded with superheated steam.
I will now discuss the elimination of thermal stratification and the effect of steam velocity. Stratification is usually eliminated after the flow stream undergoes several piping directional changes, but this is not always possible within the limits of the control system or process. Proper placement of high-energy, multi-nozzle units in larger pipelines normally prevents the formation of thermal stratification. The maximum and minimum velocity of the steam has a direct relationship with the successful mixing of the water, as velocity determines the residence time available for the water to mix with the steam. If the maximum velocity is too high, there may not be enough time for the water to mix before it encounters a piping obstruction, such as an elbow or T. The ideal maximum velocity usually ranges from 150 to 250 feet per second, or 46 to 76 meters per second.
I would like to introduce the minimum velocity limit and the often misunderstood concept of turndown. If the minimum velocity is too low, turbulence is reduced, and water droplets tend to fall out of suspension in the steam. As a rule, the minimum steam velocity at which water can remain suspended is approximately 30 feet per second, or 9 meters per second. For applications with lower velocities, proper mixing can be achieved using desuperheaters that provide a venturi or atomizing steam. One of the most overused and misunderstood concepts in desuperheating is turndown. When applied to a final control element such as a valve, turndown is a simple ratio of the maximum to the minimum controllable flow rate. Turndown is sometimes used interchangeably with rangeability, but their exact meanings differ considerably when comparing actual performance.
I would like to introduce the nature of desuperheater rangeability and the auxiliary elements to consider. Since a desuperheater is not a final control element, its performance is directly linked to the system environment. Actual system turndown is more dependent on system parameters than on the equipment's empirical flow variations. Understanding this makes it clear that even a high-quality desuperheater cannot overcome the failings of a poor system. Therefore, equipment must be evaluated on its own merits and weighted accordingly. With improvements in nozzle design technology, pipeliners are now rarely required. However, depending on the particulate quality of the water source, Inline strainers may be necessary. The previous calculations and recommendations provide the necessary information to select the proper Desuperheater design and size.
Next, we turn to nozzle technologies.
I will now introduce the criteria for selecting a Desuperheater and the first representative design, the fixed geometry nozzle design. Selection is based on various application considerations. Rangeability for minimum to maximum load requirements, minimum steam velocity, the straight pipe length and distance to the temperature sensor after the Desuperheater, steam pipe line size, and the differential pressure between water and steam. Among the typical Desuperheater designs, the fixed geometry nozzle design, shown in Figure 7.3, is a simple mechanically atomized Desuperheater with single or multiple fixed geometry spray nozzles. It is intended for applications with nearly constant load changes, with rangeability up to 5:1, and is capable of proper atomization in steam flow velocities as low as 14 feet per second under optimum conditions. Standard installation of this type of unit is through a flanged branch connection T on a 6 inches, or larger steam pipeline.
This is a detailed design drawing of a nozzle with a fixed geometry that does not change structurally.
I would like to discuss the application limits and control method of the fixed geometry nozzle design. Because the structure is simple, this design is usually not available for applications requiring large CV, meaning high-capacity injection. Additionally, since the unit itself does not have a function to regulate the amount of water, a separate external water control valve must be installed. This external valve meters the water flow based on a signal from a temperature sensor installed in the downstream steam line. In other words, it has a temperature control loop structure where the external water control valve opens and closes according to the measured temperature to determine the amount of water injected.
I will now introduce the variable geometry nozzle design. Figure 7.3 shows the fixed geometry nozzle discussed previously, and Figure 7.4 shows the variable geometry nozzle design I will explain now. The variable geometry nozzle design is also a mechanically atomized Desuperheater, but it uses one or more variable geometry, back pressure activated spray nozzles. Because the nozzle geometry is variable, it can handle moderate load changes, with a rangeability of up to 20:1. Atomization performance is properly achieved even at a low steam flow velocity of 14 feet per second under optimum conditions. Standard installation is through a flanged branch connection T on an 8 inches, or larger steam pipeline, and unlike the fixed type, it is available for large CV requirements.
This shows the design structure of a variable nozzle that can change its geometry according to operating conditions.
I would like to introduce the self-contained design. First, the previous variable geometry nozzle design also meters water flow via an external water control valve based on the signal from the downstream steam pipe temperature sensor. In contrast, the self-contained design, as shown in Figure 7.5, is characterized by integrating the function normally performed by an external water control valve into the unit itself. This internal control element has a plug that moves inside a cage by means of an actuator, which receives the signal from the temperature sensor in the downstream steam pipe. The metered water is then passed to the variable geometry nozzle and is atomized as it enters the steam pipeline.
This is an independent design method that operates on its own without external auxiliary devices.
I will now explain the performance characteristics of the self-contained design. Because the internal intrinsic control element and the variable geometry nozzle work in close coordination, this unit can control load changes from moderate to high levels. The rangeability is possible up to 25:1. Atomization performance is also properly ensured even at steam flow velocities as low as 14 feet per second under optimum conditions. Standard installation is performed through a flanged branch connection T on a steam pipeline of 8 inches, or larger, and it corresponds to moderate CV requirements.
I would like to introduce the steam atomized design. Figure 7.5 shows the self-contained design, and Figure 7.6 shows the steam-assisted design that I will now explain. The core of this design is the use of high-pressure steam to atomize the spray water rapidly and completely. Therefore, it is especially useful in pipelines with low steam velocity. The atomizing steam, usually twice the main steam line pressure or higher, meets the water in the spray nozzle chamber. At this point, the energy of the expanding atomizing steam breaks the water into very small droplets. These smaller droplets are converted to steam more quickly and allow the water to remain suspended even in low steam velocity flow, enabling complete vaporization to occur.
This is the steam-assisted design, which improves control performance by utilizing the flow of steam.
I will continue by explaining the application range and additional requirements of the steam atomized design. Thanks to the use of high-pressure steam for atomization, this design can properly mix water into steam even at very low velocities of approximately 4 feet per second, or 1.2 meters per second, under optimum conditions. The response range for load changes is also very wide, with rangeability possible up to 50:1. Standard installation is done via a flanged branch connection T on a steam pipeline of 8 inches, or larger, and it is available for moderate CV requirements. However, this design requires an external water control valve to meter water flow based on a signal from a downstream temperature sensor, and additionally, a separate on-off valve for the atomizing steam supply must be equipped.
Now, I would like to introduce the geometry-assisted wafer design. This device was originally developed for small-diameter steam pipelines of less than 6 inches, where an insertion-style Desuperheater cannot be installed. Since the structure itself is in a wafer form, it is installed by sandwiching it between 2 flanges in the steam pipeline. The key is the reduced diameter throat venturi. Thanks to this venturi, water is sprayed completely around the circumference of the wafer, and spraying occurs simultaneously at multiple points through drilled holes or small nozzles. Additionally, because the venturi increases the steam velocity at the injection point, atomization and mixing performance are enhanced, and it operates properly even at low steam velocities of approximately 10 feet per second, or 3 meters per second, under optimum conditions.
This is the drawing of the wafer design, which optimizes flow by applying a special geometry.
To summarize the performance of the wafer design seen previously, it can control moderate load changes, and the rangeability handles up to 20:1. Installation is possible in steam pipelines from 1 inch to 24 inches, and it corresponds to moderate CV requirements. However, this method requires a separate external water control valve to meter the feed water based on the temperature sensor signal from the downstream steam line. Next, I would like to introduce steam conditioning valves. A steam conditioning valve is a device used to simultaneously reduce the pressure and temperature of steam to the level required for a given application. Since these applications usually deal with high inlet pressures and temperatures and require significant reductions in both properties, it is best to manufacture them with a forged and fabricated body that can better withstand high pressure and high temperature steam loads.
Next, we turn to conditioning valves.
I will explain the advantages of a forged body. Compared to cast valve bodies, forged materials permit higher design stresses, improved grain structure, and inherent material integrity. Additionally, forged construction allows the manufacturer to provide ratings up to Class 4500, as well as intermediate and special class ratings, with much greater ease than cast bodies. Because steam properties often change drastically as a result of temperature and pressure reduction, the forged and fabricated valve body design allows for the addition of an expanded outlet. This expanded outlet controls the outlet steam velocity at lower pressures. Similarly, since the outlet pressure is reduced, the forged and fabricated design allows the manufacturer to assign different pressure class ratings to the inlet and outlet connections to better match the adjacent piping.
Now, I would like to introduce the advantages of integrating the pressure reduction and desuperheating functions into a single valve rather than using 2 separate devices. First, the inlet and outlet connections can be more closely matched to the adjacent piping. Also, spray water mixing is improved because the turbulent expansion zone formed downstream of the pressure reduction elements is utilized optimally. Rangeability is enhanced, and noise reduction is further increased due to the additional attenuation of noise resulting from the spray water injection. In some designs, response time is improved thanks to an integrated feed-forward capability. Above all, the process is much simpler since only one device needs to be installed and serviced. There are several steam conditioning valve designs that leverage these advantages, and we will cover typical examples next.
I would like to introduce the characteristics of steam conditioning valves. These valves are state-of-the-art steam pressure and temperature control devices that integrally combine both functions within one control element unit. As the need for better control of steam conditions has grown due to rising energy costs and more rigorous plant operation requirements, steam conditioning valves provide the answer. Furthermore, compared to using a separate desuperheater and pressure reduction station, they provide better temperature control and improved noise abatement while requiring fewer piping and installation restrictions. Steam conditioning valve designs vary considerably depending on the applications they handle, and each design has unique characteristics or options to ensure efficient operation across a wide range of conditions and customer-specified requirements.
This is the appearance of a steam conditioning valve, which optimizes and regulates the state of the steam.
I will explain the structure of the steam conditioning valve shown in Figure 7.8. This valve combines pressure and temperature control in a single unit. During its development, finite element analysis, FEA, and computational fluid dynamics, CFD, tools were used to optimize the valve's operating performance and overall reliability. Thanks to its rugged design, it is capable of handling full mainstream pressure drops, and the combination of a flow-up configuration and control valve noise abatement technology prevents the generation of excessive noise and vibration. The simplified trim configuration shown in Figure 7.9 accommodates rapid changes in temperature, such as those experienced during a turbine trip. This cage is case-hardened to maximize its service life.
This is a cross-section view where you can verify the flow path inside the valve and the arrangement of the components.
I would like to introduce the internal trim configuration and the spray water manifold of the steam conditioning valve. The cage undergoes case hardening to ensure maximum life and is allowed to expand freely during thermally induced excursions. The valve plug is continuously guided and utilizes cobalt-based overlays both as guide bands and to provide a tight, metal-to-metal shutoff against the seat. A spray water manifold is located immediately downstream of the pressure reduction stage. This manifold features variable geometry, back pressure activated spray nozzles that maximize the mixing and rapid vaporization of the spray water. These spray nozzles were originally developed for condenser dump systems, where the downstream steam pressure can fall below the saturation level. In such cases, the spray water may undergo flashing, which significantly changes the flow characteristic and capacity of the nozzle at operational critical points.
This is a variable nozzle that regulates the spray amount by being activated by back pressure.
I will now explain the flashing response structure of the variable geometry, back pressure activated spray nozzle mentioned earlier. If the downstream steam pressure drops below the saturation level and the spray water flashes, the nozzle capacity and flow characteristics change abruptly at a critical point in the operation. To prevent this, a spring load is applied to the plug inside the spray nozzle. When flashing occurs, this spring load forces the plug to close, thereby blocking the sudden change in nozzle capacity.
Let's look at the behavior of the nozzle and the spray water injection method when flashing occurs. When flashing happens, the compressibility of the fluid changes, and the nozzle spring forces the nozzle to close and repressurize the fluid leg. Once this is complete, the fluid regains its liquid properties and reestablishes flow to the condenser. The steam conditioning valve injects the spray water toward the center of the pipeline rather than the pipe wall, and the number of injection points varies depending on the application. In cases with high steam pressure differentials, the valve outlet size increases drastically to accommodate the larger specific volumes. Accordingly, an increased number of nozzles are arranged around the circumference of the outlet to ensure a more even and complete distribution of the spray water.
Next, we turn to steam coolers.
This is the configuration of a steam cooler designed to efficiently cool high-temperature steam.
I would like to introduce the performance range provided by the simplified trim and the steam cooler configuration that separates pressure control and temperature reduction. Thanks to the simplified trim arrangement of the steam conditioning valve, its application range can be extended to higher pressure classes, specifically up to ENSI class 2500 and higher operating temperatures. The balanced plug configuration provides Class V shutoff and a linear flow characteristic. This valve typically uses high-performance pneumatic piston actuators in combination with a digital valve controller to complete a full stroke in less than 2 seconds while maintaining a highly accurate step response. When piping dictates, the steam conditioning valve can be provided as separate components, allowing pressure control in the valve body and temperature reduction in a downstream steam cooler. The steam cooler is generally used in applications where the pressure reduction and desuperheating functions must be separated.
I will explain the internal structure of the steam cooler and the steam sparger that follows. The steam cooler is equipped with a water supply manifold, which can consist of multiple manifolds. This manifold supplies cooling water to a number of individual spray nozzles installed in the pipe wall of the outlet section. As a result, a fine spray is injected radially into the high turbulence of the axial steam flow. The combination of the large contact surface area of the water and the high turbulence in the steam results in very efficient mixing and rapid vaporization. Next, the steam sparger is shown in figures 7, 12, and 7 to 13, and it is a pressure-reducing device used to safely discharge steam into the condenser or turbine exhaust duct.
This is a sparger that applies drilled hole technology to suppress noise generated during steam injection.
This is a steam sparger that stabilizes flow through a multi-stage pressure drop technique.
Next, we turn to turbine bypass.
I would like to introduce the steam sparger and the turbine bypass system. The steam sparger is a pressure-reducing device used to safely discharge steam into the condenser or turbine exhaust duct. Figure 7, 12 is a sparger applying drilled hole noise control technology, and Figure 7, 13 is a sparger using a multi-stage pressure drop technique. The sparger is not just a discharge component, but performs several roles simultaneously. It provides back pressure to the turbine bypass valve and limits steam velocity, which allows for a reduced pipe size between the bypass valve and the sparger. For these reasons, sparger design is a critical factor in whether the turbine bypass system functions properly. Additionally, noise abatement technology can be applied to address flow-induced noise, and both the design and installation of the sparger are key elements that determine the total system noise. Finally, I will note that the turbine bypass system is a configuration that has evolved over the last few decades as power plant operation modes have changed.
I'll explain the actual role of the turbine bypass system. This system is routinely used in power plants that must respond quickly to wide swings in energy demands. A typical day of operation might start at minimum load, increase to full capacity for most of the day, rapidly reduce back to minimum output, and then go back up to full load, all within a 24-hour period. Boilers, turbines, condensers, and other associated equipment cannot respond properly to such rapid changes without some form of turbine bypass system. The core of this system is that it allows the boiler to be operated independently of the turbine. In startup mode or during a rapid reduction in generation requirements, the bypass not only provides an alternate flow path for steam, but also conditions the steam to the same pressure and temperature normally produced by the turbine expansion process.
Now, let's discuss how the turbine bypass protects equipment and what economic advantages it provides. By providing an alternate flow path for the steam, the bypass system protects the turbine, boiler, and condenser from damage that may occur from thermal and pressure excursions. For this reason, many turbine bypass systems require extremely rapid open/close response times for maximum equipment protection, which is implemented via an electrohydraulic actuation system, or EHACE, that provides both the forces and controls for such operation. Additionally, when commissioning a new plant, the turbine bypass system allows the boiler to be started up and checked out separately from the turbine. This enables quicker plant startups, resulting in attractive economic gains. Furthermore, this closed-loop configuration prevents the atmospheric loss of treated feed water and reduces ambient noise emissions.
I will summarize the components of the turbine bypass system using Figure 7.14. Looking at the equipment list, first we have the HP turbine bypass steam valves, second the HP turbine bypass control and water isolation valves, and third the EHACE electrohydraulic system. This electrohydraulic system consists of electrical control logic, hydraulic control logic, accumulators and the accumulator power system, the hydraulic power unit, the control cabinet and piston actuators, and proportional valves. Broadly speaking, there are three core elements: turbine bypass valves, turbine bypass water control valves, and the electrohydraulic system. Whether for low-pressure or high-pressure applications, turbine bypass valves are usually the manifold design steam conditioning valves described previously, featuring Class V tight shutoff performance.
This is a schematic of the bypass system, which directly discharges or recovers steam without passing it through the turbine.
I'll explain cases where bypass valves are configured separately and discuss the water control valves. Due to particular installation requirements, these manifold design valves are occasionally separated into two parts: the pressure-reducing portion of the valve and the outlet/manifold cooler section, with the cooler section located closer to the condenser. Regardless of the configuration, however, a cost-effective solution is to place a fixed orifice device, usually a sparger, downstream for final pressure reduction to minimize the size of the outlet pipe to the condenser. Looking at the rest of the equipment list, we have the LP turbine bypass steam valves, the LP turbine bypass water valves, and optionally the LP turbine bypass steam stop valves. Finally, turbine bypass water control valves control the flow of water to the turbine bypass valves. Due to equipment protection requirements, it is imperative that these valves provide Class V tight shutoff.
Next, I'd like to introduce the electrohydraulic system, which is responsible for actuating the valves. This system actually moves the valves, and its primary elements can be divided into three main categories. First are the hydraulic actuators that perform the actual actuation. Second are the hydraulic accumulators and power units that store and supply hydraulic energy. Third are the control unit and operating logic that command and manage the system's operation. These three elements work together to actuate the valves precisely and rapidly.